Okay, so welcome to the last day of CRV. I'm very happy to have our second keynote, Simon Lucey, here with me. Simon's a research professor at CMU in Pittsburgh, and he's the director of the CI to CV lab. The CI to CV lab is focused on machine learning and computer vision with an emphasis on applications targeting 3D reconstruction and shape analysis. You're about to find out soon. Simon's from Australia. He's an Aussie. You're going to hear his beautiful Queenslander accent soon. He graduated from Queensland University of Technology, and then he moved to Pittsburgh to do a postdoc at CMU, and he stayed. So he became an assistant professor there, but he returned to Australia for a short stint as an Australian Research Council Fellow. So this is an ARC fellowship, which is, for you Canadians, it's very similar to a Canadian Research Chair. And in Canada, he worked at CSIRO, which is the federal government, the Australian federal government research lab that does everything from obviously 3D reconstruction to satellites to keeping the rabbit population of Australia down. But the lure of Pittsburgh was too great, and he returned back to CMU in 2014. And I should note that there's probably an American wife involved in all of that move. So Simon's been back now for almost 6 years. He's also a principal scientist at Argo AI, which, if you're not aware of, is one of the more prominent self-driving car companies. It's really a pity we couldn't do this in person, obviously. I think one thing that I really appreciate about Simon is when he's in a room, he brings a lot of energy and enthusiasm. And it would have been great to have him there with all the students and asking questions, but we're doing the best that we can now in a virtual setting. So with all that, I'm happy to have Simon with us today virtually, and I'm going to hand it over to Simon.
Thanks so much, Michael, and thank you so much for that kind introduction. And yeah, it's a real pleasure to be here, and to actually kind of get a chance to hopefully interact with you guys remotely at least. And I had the pleasure of sort of sitting through the keynote, John's keynote yesterday, and it seemed like it went really well. So I really look forward to interacting with everyone, and it looks like everyone's having a lot of fun at the conference. Even saw that there was a banquet last night, which looked like a lot of fun. So as Michael was mentioning, I do a lot of work. I'm at CMU, and I'm also a principal scientist at Argo AI. So I'm doing a lot of work on geometric reasoning. So basically helping robots and vision algorithms try to make sort of sense of the 3D world. And so one problem that I'm really interested in at the moment is you've got sort of a street scene like this. You perhaps have an autonomous car driving down the road, and a really important part of the autonomous car sort of system is the perception stack, is basically understanding where objects are, sorry, went the wrong way, where objects are in the 3D world. So what we really want in an autonomous car is for us to be able to identify objects, not just vehicles, but vehicles are sort of a really, really important one, especially because they're moving fast, they're big, and we don't want to just detect the vehicles in the image. We want to know where they are in the 3D world. So it's really, really important for us to do that. And so there's a lot of movers and shakers in this space trying to determine how to solve this problem well. So one thing that sort of when you first come into this world is that, well, we can solve this through sensors. I could go get an autonomous car, put a bunch of LiDARs on top, and I can basically detect where objects are at a distance. And LiDAR is wonderful, and there's a lot of things you can do in LiDAR, and that space is sort of rapidly expanding at the moment. Lots of really cool vision and machine learning work going on in LiDAR. But LiDAR has its limitations, especially for objects at a distance, because LiDAR basically, the field of coverage you get from a LiDAR essentially dramatically reduces as the object is further away. You get less coverage. The other thing too, there are limitations. So black bodies on vehicles and things, and also reflections on mirrors and glass really limit its usefulness. And so people are really working hard to try to kind of make LiDAR be better at a distance and to be able to handle denser objects. But one thing we really want to do still in computer vision and in autonomous vehicles is, can we just go from an image? And one reason we can go from an image is that it's dense. There's lots and lots of pixels that we are getting describing the outside world. And what we'd love is if we could just take an input image and basically pass it through a deep network, and to be able to get back out simply two things. We'd love to be able to get the pose of the 3D object and also some sort of coarse description of its 3D size, okay? And when I'm writing this, I'm not necessarily saying the CAD model here. I'm actually just talking about the coarse points, but I'm going to include CAD models here just to kind of showcase that what the semantic meaning of these points are. And so we really want to be able to get an image, run a deep network through, be able to get 6 degrees of freedom out, describing what the object is, and also hopefully the rough 3D structure. Now, the issue is, this sounds like it should be super easy. It sounds like we have all these wonderful deep networks now, ResNet, densely connected networks. We have all these great things like mask RCNN, being able to run over all sorts of different tasks, but it still is a really, really hard problem. And one of the reasons it's a hard problem is getting the 3D ground truth to train these deep networks is really hard, and it's tedious and it's difficult. Because like if you thought sort of labeling in 2D was boring, try labeling in 3D. It gets really, really tedious. And I've got an example here of sort of what labeling in 3D looks like. This is a great example taken from Silvio Savaresi's group in Stanford. They put together a number of years ago, they put together a benchmark called Beyond Pascal. And what I love about this video is it sort of walks through really the tedious nature of labeling. Essentially, the annotator not only has to go and click on 2D points, but the annotator has to go through and actually select the 3D model that corresponds to the image and actually tries to sort of set up correspondences between the two. So for the purposes of this talk, I'm going to refer to this as 3D supervision. So 3D supervision is not just getting an image and clicking on points or drawing silhouettes. It's actually associating the image with a 3D model, okay? And so I could potentially have an image and I click on some points, but I also have to associate it with a 3D model. And so that 3D model obviously has 3D points, you've got P of them, and how you can correspond the two, it's a well-known vision technique. It's something called PNP. There's a bunch of things out there. You can, if you download your favorite version of OpenCV, you can kind of play with a version that does a good job. But essentially, as long as you've got correspondences between the 3D model and 2D landmarks in the image, you can recover the 6 degrees of freedom. And you should be able to then reproject that 3D structure back into the 2D image. Okay, so that's basically 3D supervision, but it's really slow and tedious. So one thing I've been really fascinated by is, what if we don't have 3D supervision? And there's a couple of reasons that we'd like to perhaps not have 3D supervision. One reason is it's really hard to ensure that for a specific object category, you have enough coverage of the 3D variability you're going to see in the imagery. So for instance, I'm sure many of you guys in Canada drive around in pimped out SUVs. I know I take a car like this to work every day, but you can't necessarily guarantee that the shape variation you're going to see in the imagery is going to match what you have offline. Okay, so that's really, really hard to do. So maybe for autonomous cars, you could potentially do that. But if you want to generalize this problem outside object vehicles and generalize it to objects in general, this is really, really hard to do. So what about 2D supervision? And what do we mean by 2D supervision? So basically 2D supervision is just assuming that we just have the landmarks. We have no correspondence with a 3D model. So we just have the landmarks. And so what can we do just with these landmarks? And can we actually solve some of these problems just using simple 2D supervision, i.e. just landmarks or perhaps a silhouette in an image? So this makes the task a little bit easier from a labeling perspective, because now I just have to hire people or annotators to actually go and click on 2D landmarks, which is a little bit easier. And in fact, there's a great data set that got put out at CVPR 2019 called the Apollo Car 3D data set, where they were actually able to get annotators to sit down and get correspondences to 66 landmarks per vehicle. And so you can actually kind of do a pretty good job on this. So the question is, if I can get this type of supervision, how can I then, and it doesn't have to necessarily be for a vehicle, it could be for an object category such as chair. if I get this type of supervision, how can I automatically recover the 3D geometry just from those 2D landmarks? Okay, so and people in computer vision and robotics have been working on problems like this for a long, long time. Obviously, say if I've got multiple images of the same object, say if I've got the multiple images of the same car, or multiple images of the same chair, I could apply structure for motion and recover everything. And so that's pretty easy to do. But typically, we don't have that type of scenario. What we typically have is we have tons, maybe millions of images of different instances of the same object. So it could be car, could be chair, could be table, could be any myriad of type of object. And what we want to do is we essentially want to just use this type of 2D supervision to recover our 3D structure and pose. Now in literature, people refer to this in a couple of different ways. At Georgia Tech, at a Jim Regg's group, they're starting to call this 3D lifting. So lifting 3D structure out of 2D, just from a lot of images from the same object category. A couple of years ago, we tried to emphasize a different term. I kind of like it, but again, it's whatever's catchy amongst the community. I like to use the term structure from category. So sort of meaning that it's kind of like structure for motion, but you don't have knowledge that the object you're trying to recover is rigid. You don't know it's the same object. It's actually different instances of the same object category. And so what we want to do to kind of describe the problem a little bit more formally, essentially, and it relates to a lot of other work that's been done in computer vision, specifically something called non-rigid structure from motion. And so typically when you hear non-rigid structure from motion, you think to papers of people dancing around in leotards, trying to track kind of 2D landmarks and trying to recover the 3D structure of perhaps a person or a face. And typically in these problems too, they incorporate time. They know how something's going to move in time. So in this problem that we're trying to study, structure from category or 3D lifting, we have no sort of semblance of time. We just have knowledge that we have a large ensemble of images with 2D landmarks, and we just want to lift the 3D structure and pose out of those landmarks. But it is related because the idea of structure from category is very much a non-rigid structure from motion problem. With the idea that you can think of the object category itself as a non-rigid object. So none of the individual instances of the chair are, each individual instance of the chair, sorry, is rigid, but the object category itself is non-rigid. So you can kind of pose it in this way, but just relaxing any temporal constraints you can typically use. So how do we formally describe this problem? Well, let's have a look. We can take a closer look and we can kind of say, well, we want to get back a 3D coordinate, X, Y, and Z, and we have a corresponding 2D coordinate in the image. And so what we want to do is we want to basically relate the two via a camera projection. And so the camera projection is obviously related by the parameter theta, which describes 6 degrees of freedom. It can be twist parameters or whatever you want to kind of, however you want to parameterize the camera. And we can then basically kind of form these into matrices. So I've got my W matrix here, which has P points, and I've obviously got 2 measurements per point. And then for the 3D structure, I obviously have 3 measurements per point. And so the problem basically boils down to, I want to project my 3D structure, S, through a projection function, pi, that basically is mapped down using theta, which is the camera, to recover W. And so we refer to W as the 2D correspondences, we refer to S as the 3D structure, and we refer to theta as the camera. Now, what makes this problem so hard is that we only know W. So when we're doing the 3D lifting, it's completely unsupervised from a 3D perspective. We only have the 2D measurements. And so you can kind of see that this is inherently an ill-framed problem. So I've got perhaps 2P knowns per example, but for every example, I've got to recover 3P unknowns plus 6. 6 is obviously for the 6 degrees of freedom for the camera. So in a problem like this, I need to be able to constrain it because there's no way that I can solve this just through a simple solver. It needs to be constrained. So we know a lot of things about camera matrices now. So in particular, if we know that something's coming from SE3, we essentially know the rotation matrices have to live in SO3, so they have to be orthonormal. But we also, that's not enough. We need to somehow constrain the 3D structure. And so the question that really kind of this boils down to is, what should that constraint be? And more kind of importantly, can I potentially learn it? And sort of the crux of 3D lifting is, can I actually learn it solely from 2D supervision? So I don't have any other 3D knowledge about the object. Can I somehow go through and just go through the 2D examples and learn this redundancy in S? So is that feasible? Is that possible? Now, if we go running back into history, we actually kind of can see that this is actually possible. People have actually attempted this in the past. Probably the most famous version is, let's say we take a chair and the chair has P points, there's X, Y, Z coordinates there. And let's say I vectorize this S. So I kind of make it a nice long vector instead of a matrix. A really simple idea that sort of dates back to a really famous paper by Chris Bregler, sort of kicked off non-rigid structure for motion. It was in CVPR 2000, was basically to say that this S vector, so this flattened 3D structure, can be represented by a combination of just a few dictionary vectors and some coefficients. And so obviously, if you have less degrees of freedom in the dictionaries, you can find some redundancy that can help you solve this 3D lifting problem. More recently, this idea has been seized upon by quite a famous paper now, Dai et al. It came out of Hongdong Lee's group at ANU. They won best paper for this method at CVPR 2012. And so they generalized this approach. And what was really cool with it too is that they solved some of the open issues over, well, how many dictionary elements do I need? How big should the rank be? And so they actually came up with a really elegant way of solving that. And so for a long time, that became sort of the standard method to use for this 3D lifting problem. And so we'll refer to this herein as the low rank shape prior. So that type of assumption. So the low rank shape prior, unfortunately, it works really well for faces, sometimes for bodies, some toy types of object categories. But as soon as you start scaling up to say millions of images or lots and lots of shape variation, it's not very suitable for this 3D lifting process because it's so limited in terms of its expressibility. So, and you can kind of see an example of it here. So this is an example of running sort of the Dai et al. Stuff over the problem of lifting chair structure out from 2D labels of chairs. And so you can kind of see that it does an okay job, but it's a bit wonky. The 3D structure's off. It's surprisingly good compared to, say, just hitting this with just regular structure for motion. That doesn't work very well at all here. But what we've recently proposed, and this was shown at ICCB 2019, is a brand new way of solving this that can get really good results and it can scale up to millions and millions of images. And so, and this is something that we presented at ICCB 2019 called Deep Non-Rigid Structure for Motion. And for those of you who are interested, there's now a new PAMI paper that's done, that's an extension of this. It's just been accepted. And so what's really exciting about this is that it really opens up the opportunity for us to look at this 3D lifting problem for a whole range of object categories. And I'm going to try to kind of go through today and convince you of why this is perhaps cool and perhaps why some of these ideas could be applied to other problems in robotics and vision. So obviously one thing we could do if we want to kind of increase our ability to model more and more complex shapes is to make the dictionary overcomplete. And what I mean by overcomplete, let's just add more column vectors to the dictionary. Okay, so that seems kind of obvious. So I can actually have more flexibility in terms of modeling the shape. But obviously that comes with a problem because it's not unique. The solution is no longer unique because the whole benefit of low rank was that you could actually create a unique system because you're throwing away a lot of information when you're going from 3D to 2D. So that's not really going to help. But the idea of going over complete to expand your ability to model shape variation is a good one. So if you can actually kind of introduce a little bit of a tweak, and the tweak is this: enforcing that the code vector is sparse. Okay, so rather than it being low rank, you can actually enforce that the code vector only has 1 or 2 elements ever active during any one example. And so an example here is sparsity 1. I could jump around and do different elements, but only 1 element is ever active when I'm trying to reconstruct S. Now, sparsity 1 is sort of extreme, because what happens is that I almost need to really have a very, very large matrix just to model anything. So a nicer strategy is to relax this a little bit and just introduce sparsity. Okay, and we're going to refer to sparsity as just basically enforcing that this vector B has to lie in the set C. And you can kind of visualize what C looks like. So C is basically kind of enforced by enforcing 2 convex constraints. One is that it's non-negative, and I'll come back to why we want non-negative, but just sort of believe me for now, that's a useful thing to have. But the more important one is sparsity, this L1 penalty. And so the L1 penalty has been well known to approximate sparsity. And we won't get into that, but it's a nice tool to use, and we can use that to add as an additional constraint. So this seems like a really promising idea. So we could actually have a more expansive dictionary so I can model more shape variation. And in fact, we introduced this as an idea. We referred to this as a sparse shape prior. And so the overcomplete dictionary increases complexity, and the sparsity constraints guarantee uniqueness, so that you can actually make sure that you get a unique code back out when you reconstruct from 2D to 3D. And we presented this work at CVPR 2016, and we actually, around this work, we actually had an NSF grant that was funded under this work too, that demonstrated how to introduce sparsity for recovering 3D structures when you want to have a lot of expressibility. And so the cool thing with it is that it actually works pretty well. You can actually do a really good job of reconstructing things, but there's a caveat. The more shape variation that you want to model, you need to add more and more columns to the dictionary. And as you add more and more columns to the dictionary, what tends to happen is that nearby dictionary columns start to get very, very close to each other. And that introduces instability. Okay, so sometimes the system gets confused. Oh, should I use this vector? Should I use this vector to model it? And so if they're too close, they can get confused. Okay, and so what was frustrating with this is that I tortured some PhD students over this for a year or two, because I was believing so thoroughly that this is the way to solve this problem. But inevitably, and this is what always happens, and I'm sure supervisors can attest to this, is that the students were right. And basically the system was way too sensitive to noise. So as soon as we started to try and model any type of shape variation that was interesting, if you started introducing noise, and this is what sort of this x-axis here is, it's basically the noise ratio. And you can kind of see here that the blue line here is our approach compared to the low rank prior. But as soon as you start adding noise, it just sort of drifts back to this low rank solution. And so any benefit sort of disappears. And this is really important, this tolerance to noise, because if you're relying on human annotators are going to be noisy. There's not going to be they're not going to be able to always kind of put points in the right spot. So robustness to noise really is the name of the game here. So in a way, this was really theoretically interesting, but practically we couldn't really use it for this problem. So it got us thinking a little bit about, but how do we measure instability in dictionaries? Okay. And so it turns out that if you read a lot of signal processing literature and things in compressed sensing and fields like this, there's a measure that they like to use. And it's a measure called mutual coherence. And so mutual coherence, again, you can get caught up in the math. The math is sort of the mathematical equation here is shown here. But again, I'm visual and I like thinking about things visually. And so basically the idea is this, is that you want to ensure the mutual coherence basically is it wants to measure the closest angle between any 2 vectors in your dictionary. Okay, and so your mutual coherence is bound by this. So whatever vectors are the closest, that dominates your mutual coherence. And it kind of makes a bit of sense, again, because if things are very, very close together, any bit of noise can cause them to have some confusion. So what you kind of want to do is if you want to kind of optimize mutual coherence, you want these vectors to be as well spaced as possible. Because if they're better well spaced, you get a more tolerant solution. Okay, so just a pretty simple idea. Now, what's nice also too is in compressed sensing literature, there's a really cool lower bound for mutual coherence. And some of you may be aware of it, some of you may not be, but it's something called the Welsh bound. Okay, so the Welsh bound is a non-zero constant, so it has to be greater than 0. But what's really cool with the Welsh bound is the Welsh bound can give you the lower bound on your dictionary without having any knowledge of the weights. All it actually is dependent upon is the structure of the matrix. So when I say structure, structure could simply be perhaps the number of rows versus columns. Or if you want to kind of, and we'll get into this in a little bit more detail, if you start zeroing off parts of the matrix, you know, you can actually sort of start adding arbitrary structure to the matrix. You can actually control this lower bound on the mutual coherence. And so what's really cool there is before you do any type of learning whatsoever, you can actually impose certain amounts of structure on a dictionary before you do any learning. And so this can be useful because then you can actually control robustness. And so this idea of the Welsh bound is really, really useful. And in fact, we have an oral at this CVPR where we actually talk about how this idea can be connected to deep learning and how you can potentially predict different network architectures in terms of the generalization performance simply by looking at this Welsh bound. And I'm going to talk a little bit about that, not too much. I'm going to talk a little bit about this as the talk goes on. So, but again, it's a Friday. People don't want to get too mathy. So let's just think visually about what we're talking about. So what the Welsh bound really is about is it's basically kind of saying, you know what, if I've got a dictionary and it's more square, meaning that the number of rows is closer to the number of columns. Obviously, if it's overcomplete, the number of columns has to be more than the number of rows. But if it's a little bit more square, what the Welsh bound kind of says is that more than likely when I do some learning, the system will be more robust, but it's going to have less capacity. I'm not going to be able to model as many interesting shapes. If I want to increase the capacity, if I want to add more column vectors to D, I can do that, but that comes at the cost of it being less robust. And again, if we think back, if you think about these dictionaries sort of living in a circle, if you add more and more dictionaries, and you want them to be equally spaced, the angle has to come down as you add more and more elements. So there's this trade-off between capacity and robustness. And that's one thing we've been seeing time and time again in these classical methods for 3D lifting. So one question that we've sort of been pining over here at CMU for a couple of years is, can we do better? Can we do better than sort of getting caught by these two extremes? So, and this is sort of a crazy idea, but one idea, and we kind of leveraged this from some ideas going on in sparse coding at the moment, is can we actually artificially make the D more square, your dictionary more square? And so one way to do that is actually, let's get my observation S. Remember, S is my vectorized version of the 3D shape. And one thing I could do would be just to artificially add zeros to the end of S. I just artificially add zeros to the end of S. And what's kind of cool with that, again, it seems kind of weird. It seems sort of arbitrary. And in many ways, it doesn't have to be 0. It could be any kind of constant. You could kind of basically put anything you like in there. But what's kind of cool is by doing that, you make your dictionary more square, okay? And so you might go, well, why would I want to do that? Well, one thing is that by making my dictionary more square, I automatically lower the bound of mutual coherence, which is, again, is some sort of proxy for kind of saying how robust I am to noise. The second thing too is intuitively, it kind of makes sense. So if you're trying to pack in a lot of vectors into a circle, if you add more and more vectors, you're running out of space. But if you add an extra dimension, so go from a circle to a sphere, all of a sudden you free up space. And so you can actually allow the vectors to spread out so they're more robust to noise. So one issue with this, however, is if you arbitrarily sort of extend S with zeros, you sort of rapidly increase the number of parameters in D, almost unnecessarily. Like you sort of go, wow, I have this big increase in the number of parameters in D. So one thing you can do is actually, you can keep the matrix square, but just sort of strategically zero out parts of D such that you can keep the parameter count low. Okay, so you want to kind of, again, you don't want to necessarily explode the size of the dictionary. You want to keep the size of the dictionary reasonably low, but you want to see if you can have a structured dictionary that's square and still obeys these nice properties. And so it turns out there's a very strategic way of doing this. One way to do this is to actually enforce a lower block triangular form for the matrix. Okay, so you can kind of see here that we have a top matrix here, D11, D22, D21, and we have this big area here that's turned off. Now, there's a couple of reasons why this is advantageous. First off, as we'll talk about really quickly in the next slide, it lends to a really computationally efficient solution. The second thing is conceptually, it allows you to think about B not as one single vector, but B as sort of a hierarchy of B's. So you can see that sort of D11 is dependent upon B1, but B2 is dependent upon both these vectors. So you kind of get this hierarchy being introduced. So now one thing also that you can immediately put your arm up and kind of say, well, all right, this is all well and good, but as you make D bigger, it's going to be really computationally expensive to solve this sparse coding problem. So this is another really kind of cool result. And again, this is not my result. This is from someone else's brilliant work. But I love talking about it because I don't think enough people know about the result. So this sort of cool result sort of stems from, if I have a problem like this, a sparse coding problem, so I want to recover B and I have D and S, I can typically use a standard package to solve this. And so there's a bunch of algorithms out there, things called FISTA, ISTA. You can solve it as a convex optimization problem, but there's a really neat, efficient way of solving this. It's called threshold pursuit. And so threshold pursuit turns out to simply get S, multiply it by the transpose of D, and apply ReLU, which is really, really cool. So basically, a very, very fast shortcut solution to that problem is essentially S multiplied by the transpose of D times ReLU. And you can think about ReLU. ReLU is a nonlinearity, but it's basically enforcing the constraints we've been talking about. It's making sure things are positive, and it's making sure things are sparse because it's turning things off. Okay, and if you want to delve into the details, you can show under what conditions these two things exactly match. But what's interesting too is that, and this is the ReLU nonlinearity. Hopefully everyone's aware of this. People talk about ReLU all the time. And what's really neat, but it does relate back to this idea of mutual coherence, because the better the mutual coherence of D, the better that approximation. So why is this interesting? So now what I can do now is I can take this idea of taking a sparse coding problem, such as I've got S and D and I want to recover B, and I can efficiently solve it using a feed-forward network. Okay, and so take note of the colors here. So S and S are the same here. B and B are the same here, but I'm now expressing this D matrix here as a brown arrow. Okay, so basically this is relating essentially the multiplication of S by D transpose followed by ReLU. Okay, so now we can think of this B vector that I'm solving here as almost like a hidden unit in a deep network. Okay, so that's an interesting connection. Again, that's not my connection. That's something that's been sort of touted and a connection shown, but it's neat because the reason my lab's interested in this is that I think there's a lot of black box thinking with neural networks, but there's a lot of really good theoretical understanding of what's happening in sparse coding. And this acts as a bit of a bridge. You can bring some theoretical results into deep learning to kind of do some interesting things. So what's interesting with this too is that, okay, well, let's go back to our structured example. If I have a structured matrix, what that turns into, especially if I have this lower triangular structure, it turns into a multi-layer deep network. And so you can kind of see here that the colors relate to the different components, and we can actually kind of keep on expanding this. So if I add more and more structure, I have more and more layers. And so what's neat here is I can actually now have a mechanism to relate network structure to a single matrix. I can go backwards and forwards between the two. Okay. Now, obviously, you would never computationally, you would always do the feed-forward network. It's much faster to do this. You don't want to solve the sparse coding problem. But what's cool is that you can reinterpret the deep network as a structured matrix from a sparse coding perspective. Now, why is that interesting? Well, we actually recently, again, I'm talking about this, this oral we have at CVPR, we kind of looked at this for some visual classification tasks and demonstrated that you can take things like AlexNet, ResNet, and DenseNet and view them as structured matrices. And so what's interesting is then if you go and analyze the Welch bound of these different network architectures, it turns out that there's a very strong correlation between the Welch bound and the networks that generalize best. And so we actually have a neat result here with the Welch bound and the number of parameters you have in a network, and actually the validation error you get on, say, a benchmark like CFAR10. So again, we're not pretending for this to be a grand theory of deep learning, but what we are sort of saying is that this connection with sparse coding is perhaps one that could be utilized in a couple of different ways, and it's definitely interesting. And so, and we're excited to kind of talk and present more on this work at CVPR. But getting back to our original problem, what's cool by establishing this connection now is I can now think of the 3D lifting problem as actually building a 2D autoencoder with a slight twist. Okay, so a slight twist that the 2D autoencoder takes the 2D labels, runs it through an encoding scheme or an encoding layer, and then it's able to decouple the camera, which is theta, from those coefficients and then reconstruct S. Okay, and what's neat is that we can do this all under the view that this is approximating a sparse coding problem. So because it's approximating a sparse coding problem, it's way easier to work out how I should factorize the camera from the coefficients and decouple everything. And so it's a very, very powerful mechanism for doing this. And so this is at the heart of the idea of deep non-rigid structure from motion. So we basically tried to write down the problem of 3D lifting as a factorization problem, and then show theoretically how you can solve it efficiently through deep networks, and that there's a theoretical connection between the two. So what's really cool too is that in the paper, up until we published the paper, there really wasn't a lot of work out there on 3D lifting. It's really this last year that people have really kind of got into this problem. So up until then, there was a lot of sort of non-deep learning methods out there. And what was really exciting is that when we try to solve this problem on something like the IKEA data set, which have different object categories like bed, chair, sofa, table, you can kind of see we've got this busy chart here, which I don't love. It's like got lots of details in here. So don't go into all the details. You can come back and watch the video and have a look later. But you can see all these papers out here. But what's really cool is that the y-axis is a log scale for error, okay? And so what's very cool is by applying the strategy to 3D lifting, we not only outperform all the leading methods, we outperform them by orders of magnitude. So, and one thing that's very, very cool, so that's one thing that got us very excited. So it's not just sort of 10%, 20, it's like orders of magnitude, problems where this regular non-rigid structure from motion just failed, just wouldn't work. This idea of sort of making sure that these dictionaries are more square whilst entertaining larger capacity really kind of seemed to kind of connect well with the problem. And you can see like an example of ground truth, ours, and the next closest technique. What's also really interesting too is we analyze things in terms of noise, because we know that when people are annotating things, vehicles, chairs, other things, there's going to be noise. And so what was really encouraging too is that when we analyzed this, our reconstruction errors were dramatically better than the other methods, but it still remained dramatically better even when we compared to the other methods without noise. And so again, hopefully you guys can go through the details after the talk, but it really comes back down to this idea of lowering the Welch bound, making sure the Welch bound on this dictionary can be as low as possible. We also did some interesting things in terms of missing data. So a question that we oftentimes field in this problem of 3D lifting is, well, how does this work for a chair? Some chairs have 8 points, other chairs have 12 points, other chairs have 20 points. How do you handle that? So you definitely have to have some idea of correspondence, but you can handle that pretty easily by treating some points as missing. And oftentimes too, in images, points are missing because of just self-occlusion, like with the vehicle. There's always one side of the car that's always missing. And so what's really nice too is our method handled missing points very well. And again, you can handle missing points by just sort of going to the factorization problem and just masking out the components that aren't there anymore. One last thing too is this connection with sparse coding is interesting because for many problems in 3D lifting, you will not have 3D ground truth. So you will not have a good sense over whether your 3D reconstruction is a good one. All you've got to go off is the 2D projection error. So what's really encouraging too is once you do 3D lifting through this process, you can go through and have a look at the mutual coherence of the dictionary you learn. And what we found is that the mutual coherence is highly correlated with the ground truth 3D reconstruction error. So if you go through and you've got a data set where you have no 3D ground truth, you can go through and apply this technique, learn it, and then look at the mutual coherence. And you can kind of get a gauge for whether the reconstruction's been a good one or not. Again, based on how close these dictionary elements are to one another. So here are some other kind of visual examples of sort of planes, kind of recovering here. Again, oftentimes get the question, are we reconstructing the white structure here? No, it's just the 3D points. And we're just using this white structure here to visualize that it's a plane. Bikes. And what we've also done recently is we've been thinking about the issue of perspective cameras. Okay, so how do we handle perspective cameras and with realistic occlusions? So occlusions where you've got a lot of annotator noise, you've got things that are missing. And so we've done an extension to Deep NRSFM that's now an archive. It's called Deep NRSFM++. Again, we didn't want to be left out in this ++ game, so we thought it made a lot of sense to add ++ to our own algorithm. And so what's cool is that if you revisit the problem that I spoke about at the beginning of the talk, where you've just got coarse 2D landmarks and you're annotating them, you can get very good reconstructions just from these landmarks. And this is a comparison between our latest technique and the older technique. So for this problem, the original technique for the ICSV paper, it could only handle weak perspective geometry. This one could handle perspective, and that really helped, along with some other kind of improvements. Some other kind of cool things is that we applied this to reconstructing human bodies. Again, with human bodies, it's a sort of a toy problem because it's typically ground truth, but it's a great way of benchmarking how well your algorithm goes. And what we did recently is we can kind of showcase here. Now, again, this technique uses no time. There's no temporal constraints used here. So typically when you're doing reconstruction of bodies, you're using time. This is frame to frame. So you could jumble the frames and still get this type of reconstruction. What we did also is, and I probably will maybe get this question too, in the last 12 months, there's been more and more work done in 3D lifting, and probably one of the best known methods in 3D lifting at the moment is something called C3PDO. And other than being really jealous of not having a Star Wars reference in the title of our method, the technique actually works really well. And it's a paper out of Oxford, Andrea Baldali's group, very, very cool work. And Andrea's work scales well too, but our latest stuff does seem to kind of solve some of the problems that he was perhaps facing with some of that work. And we can include perspective geometry, with many of these other techniques cannot. And then we've done things in like sort of different object categories. So Pascal 3D. So here we've got an example of chair. Again, you can kind of see what's visible, not visible. We've got examples of buses, reconstructing a bus. Again, what's visible, not visible, just through human annotation. And all we're doing is we're just leveraging the knowledge of the object category. That's it. And then now limitations. Obviously, all professors like to say our methods are fantastic, it can solve anything. There are still inherent limitations on this approach. One kind of limitation at the moment is that we can't handle ambiguity very well. So typically there is natural ambiguity with respect to sort of whether an arm can be forward or backwards. And typically you can use time and other things to overcome that. But if you throw that away, there is that inherent ambiguity. But we've been doing some interesting work to kind of try to rectify this based on connecting it to appearance and doing other things. Some other limitation too is with respect to perspective geometry. it sometimes gets confusion between deformation and perspective effects when the data is limited. And so, and you can kind of see that there. So that is a little bit of an issue as well. So in summary, again, you guys have all been a very good audience. So thank you for everyone listening. It's been serene. Summary. So we've presented a new approach for 3D lifting that uses only 2D supervision. And hopefully you guys have got a good sense over what I mean by 2D supervision. Secondly, we've been actively pursuing strategies where this theoretical connection between sparse coding and deep learning can be leveraged more. And so probably I spoke about the CVPR oral, but there's this other neat paper I'd point you guys to where we showcase some problems where deep learning does a really bad job of solving some inverse problems. And sparse coding can do a much better job, especially using these same tricks. And so we've got some really neat results, and that's in CVPR coming up. We've also kind of done some interesting work on how 3D lifting can be used for learning appearance detectors. So that example of sort of the ambiguity over whether a hand's forward or backwards. If you perhaps somehow condition on the appearance, so for instance, my wrist looks different this way than this way, condition on the appearance, perhaps that can be solved. And so we had a paper just at ICCV that sort of leveraged some of those ideas. And then finally, and I know we're probably going to get some questions on this potentially, dense 3D lifting. And so an obvious answer to the question, are you working on it? Yes. Is it hard? Yes. And we've got some work in this space. So I just sort of introduced a link to something we did in CVPR 2019. Yeah, I'd like to perhaps sort of wrap up there and see if there's any time for questions. Thank you very much.
All right, thanks, Simon. That was a fantastic talk. I already see questions coming in, so you're gonna see my glance kind of change. I have two computers here where I can read some of the questions. So you got a couple cools going on. I think in particular where you're making the connection between sparse low-rank matrices, these banded matrices, and these different deep networks. So let me start with a couple of questions already posted. So one, and unfortunately, the ability to find where it is in your slide. So here's one is, I have another, let me see, hold on, sorry. So this is from Ren Chung. It says, when you were talking about expressing this matrix S, can I regard B as the eigenvalues and D as an eigenvector coordinate basis for S? So I think he's trying to think of a way. So if you don't mind, Simon, if you could pop back in your slides there. I think
no problem. And good question. So let's go back to where I'm at, perhaps like the original form of the problem here. Okay, so in the original connection here, let's kind of start. Let's start even here. So a good way of thinking about this is this good old PCA. Okay, so if you basically had, so I've got one instance that I'm trying to reconstruct S using these dictionary and these coefficients. But you can think of, if you had a bunch of these S's, okay, and you just wanted to determine D and B, and you had S's, you could just basically do an SVD on these S's. And so D would basically correspond to the orthobases that you get from the SVD, and B basically are the coefficients that you're using to kind of put these two things together. Now the one thing I'd put in here, oh, sorry?
No, go ahead.
And the one thing I'd kind of put in here is that in that PCA example, we make the assumption that each of these D column vectors are orthonormal to each other. So basically the inner products are 0. In this example here, I'm not making that assumption because a low rank assumption doesn't necessarily need that. And the reason that we don't make the assumption is as soon as you get into overcomplete bases, so you get, if you have more columns than you have rows, the whole idea of having an ortho basis goes out the window, okay? And so that's why, in a way, kind of one idea of like mutual coherence is if you've got the same number of columns as rows, the best way of having good mutual coherence is to make sure that all the vectors are orthonormal. But as soon as you start basically having more columns than rows, then essentially the mutual coherence is a much more sensible way of dealing with this.
Okay, so a follow-up question also from Ren was, I have another question, can we apply this threshold pursuit for solving the bundle adjustment problem? So you have this big sparse T transpose can be regarded as the Hessian matrix, and S is the residual bias. Have you put any thought into that?
Should ask him if he's interested in doing a PhD, or if he's.
Yeah, as I was going to say, it sounds pretty good. It sounds like another paper.
Yeah, so it's a really, really good idea. And so there are some issues with threshold pursuit. And so one thing with threshold pursuit is that it's not really solving under certain circumstances. It can approximate things well. So like a great example is this, is let's say I've got a least square system. If I've got a least square system, I could have, say, S is equal to dB, like we've written before. And with the least square system, I can always solve for B by just basically getting B is equal to the pseudo inverse of D times S. I can always do that. So I can always have I don't have to solve the optimization problem. I can always just express it as a single deterministic equation. One thing where this all falls apart and why this is hard for SLAM or bundle adjustment is as soon as you add constraints. So if I add a constraint to a least square system, I can no longer do that. So if I add sort of some other constraint to the system, I can't have a shortcut that way. So threshold pursuit is really, really cool, but if you want to add constraints or do extra things, that's where it becomes problematic. And in fact, that's actually where we argue that deep learning isn't sometimes always a good way to solve a problem. So SLAM is a great example because they've got lots and lots of constraints. And so we're kind of arguing in our group that that's where it's maybe beneficial to think about deep learning as a sparse coding problem, because then you can actively enforce constraints. But it's a great question.
Okay, I have another question for you. This one I believe is actually from Liam. So you were making this connection, you showed us a very nice trick where the feed forward is equivalent to this the pursuit. The question is, does this connection between the Welsh bound and deep networks only apply for networks with ReLU activation function?
Really good question. Okay, so at the moment, the answer is yes, and what Liam is kind of referring to is sort of there's other types of nonlinearities we use in deep learning all the time, like leaky ReLU and many other types of nonlinearities. And so at the moment, the connection is closest for ReLU, and so that is true. However, there does seem to be a lot of evidence, and when we kind of do things empirically using other nonlinearities, we still get very, very good results. And in fact, we're working on something where we can kind of generalize this a little bit more. The connection between sparse coding and ReLU seems strong, but if you sort of generalized this a bit more and said, well, my codes don't necessarily need to be sparse, but they have to obey some other high dimensional manifold, then you can have a connection to other types of nonlinearities. And so ReLU, yeah. But the one thing I like Liam's question there. The other thing I kind of think is the other reason I like this connection is oftentimes when you take a machine learning class or a vision class, ReLU is typically, the motivation for using ReLU is essentially so that we don't get saturating gradients. That's the main motivation. And the other thing I like about this is that this gives another motivation, that gives another connection, perhaps why ReLU might be a nice nonlinearity to use.
Yeah, and I agree with your prediction that other things are going to work, other activation functions, because most of them will act like ReLU. They're all somewhat variations on. I mean,
you can kind of, if you play, and that's one thing we've been looking at. You can, if you do enough massaging, you can kind of make leaky ReLU work like ReLU, because you can just do combinations of things and make that happen. So, but it's a good question. It's a good question, but I would say I don't want to overstate things. So I'd say the connection is strongest between ReLU and sparse coding.
Okay. A couple more questions here. So here's another one also from Ren. I think he is looking to the PhD. Another question, does the camera projection theta play a role in the learning process, and how?
Yes, so that's a good question, Ren. I deliberately kind of obscured that a little bit. So in the connection makes a lot of sense when you do weak perspective geometry, because with weak perspective geometry, you can express the camera as a linear transform. And so things can get neatly absorbed into the framework. Things get a bit more complicated when it's perspective geometry, and that's what the deep NRSFM++ paper kind of explored. But if you checked out either one of the papers I was talking about, you'll kind of see the connection. But But again, in the interest of clarity, I kind of left that component out. But when you're kind of using a weak perspective camera, you can express that linearly, and so everything can be absorbed into the linear system. So all the constraints still hold.
Okay, and one more question for our room, Sid, is nice talk. How the labeling 2D supervision could be effortless, less tedious without sacrificing performance. Is point labeling, car behind the truck example, active learning?
Yes, that's a great question. So one thing we've been thinking about a little bit too is that could you do something, say, like where, say you got a big data set you've got to label. Could you label perhaps 10% of the data set really kind of heavily, kind of go do every point, and then potentially do this, build up essentially what's essentially an autoencoder of 3D shape, and then when you do the other 90%, could you use that to kind of bootstrap the effort such that you don't need to label all the points, or it can kind of help you predict the points as you're doing it. And so over time, you could actually more rapidly label things up. And so that's one thing we've been exploring. The other thing that's interesting too is that for certain problems, so like with the vehicle example, you can use things like ground plane. So if you have knowledge of the ground plane, you can introduce that as an extra constraint. And another thing too is time. So for instance, if you're gonna label cars in time, you could label one up heavily. Then after that, it's this basically sixed off between things, no matter how many points you have. And so you could actually use those constraints to kind of help you. And so yeah, I think, and that's one thing, hopefully we're not giving away all our good ideas, but that's one thing I think that this could actually have some real juice with, is perhaps at the moment it's just so difficult to get good 3D labels, and kind of could we also utilize some of these ideas to bootstrap that effort to make it much more efficient.
Good. So I have a question. I think I get the courtesy or the privilege of asking a question because I'm the chair of this. Can you go back to your slide where you actually show your structure? This is probably the slide that you'll show. I believe it was the ICCV paper this year, where you actually show the structure of your network. So you did a very nice job setting everything up as a linear system, and then you say, well, this is really just a feed-forward network. So this is probably much further down.
Is it this one or?
Yeah, no, sorry. It was actually, I think it was all blue, and it was when you were showing us the results actually directly from your paper that you're publishing. Probably the presentation you're going to give at CVPR this year. Yeah, this one. Sorry, that one right there. Was that ICCV or sorry? Slide 51.
CVPR? This one.
Slide 51.
Slide 51. Sorry.
Yep.
Yes.
Yeah, so here's my question. So watching what you were doing. So yeah, so there's your W. Okay, so my question is, you built this as a feed-forward network. So we do all this nice work looking at this thing in linear algebra, but then your actual implementation is a feed-forward network, and you're using this auto-encoder, decoder structure. And so I'm assuming in this case, what you're doing is you're learning these weights through the training of the autocoder, decoder. So yeah. I'm guessing when you compute your Welsh bound, when you apply all this, there's a formula that this naturally can just be immediately constructed into a matrix.
Yes.
And with that said, and I assume for your case, because I can kind of see this banding of the matrices, how each layer is getting smaller and smaller.
Yeah.
But when you were looking at some of these other network structures like ResNet and AlexNet, and things that we learned. So as soon as you mentioned this sparsity and you're showing these examples and you put in these zeros, the first thing that popped into my head was dropout. I mean, yes. It's just, I'm looking at this thinking, wow, this is we've seen this in another form. So I'm just curious, when you do that mapping, in that case, I guess you're more liberal on how you can pack like an AlexNet into a matrix to do the Welsh bound?
Yeah, so it's actually not too, that's a really, really good question. And so it's not too onerous. So I can go through like very quickly, like, and I think like one example would be,
yeah, and that slide would be great, yeah.
Say here with AlexNet. So what you can kind of see here is that people are probably very comfortable that you perhaps have weights for each of these colors. So you'd have like different weights for each of these colors, and the blocks here are the hidden units that you're reconstructing. And so What's interesting here is that when you want to form the matrix, very, very simply, all you do is basically get the transpose of each of these matrices here and just stack them in this way, especially for a chain matrix. But there's one special caveat here. This little part here, what we put here is actually, and I'll see if I can do something funky because I didn't have it here, is you can actually do a negative identity matrix here. Okay, so this is actually a negative identity matrix. And so what this is the constraint that the subsequent layers have to be equal to each other. And so what's neat here is that if you wanted to kind of just if you wanted to just basically build the matrix, especially for just a feed forward chain network, you'd literally get the transpose of these, block them together into the matrix, and then have a negative I along here. And so what's interesting, but then is you can actually do this in different ways. And so you can think of skip connections and other things as just basically adding identity matrices in different parts of the matrix.
No, that makes total sense. That's right. That makes total sense. So skip connection, you're just bringing another part over, so you have an identity just to copy that over.
And so what's kind of cool is what's weird is, well, why do dense nets work better than regular feed forward networks? And there's a lot of debate, but empirically they work really, really well. But what's nice with this recent work is that this Welch-bound connection can help predict perhaps which network architectures work best without actually having to do any learning. So that's kind of cool because you're just looking at the structure of the matrix.
Yeah, very cool. So there's a last question here, and I think we should wrap up because our time's up. But let me ask it, and we can finish on this. So this is from Christopher. It says, "Thanks for the interesting presentation. A follow-up to Michael's question: are there other ways in which we can enforce sparsity in our neural networks during the optimization process?"
Yeah, for sure. I mean, one thing you could do, for instance, is
sorry, just because I think the way he has a follow-up question that's probably related, because the way Google Chat only allows so many characters. So he says, are there other ways you can enforce sparsity, or are you proposing to compute the Welch-bound throughout optimization to evaluate the model sparsity? Okay, and now you answer.
Yeah, that's a good one. So so I guess like one thing. So I'll take the question in two parts. So I'll take the second part first. So why is the Welch-bound stuff interesting? Well, first off, I think the theoretical connection is interesting because sometimes you can't tell where innovation is going to happen, and just by looking and attacking problems in different ways, you might sort of break open different directions to innovate. And so. So, as I said, I think some of these connections are interesting that we've established, and we're still not sure what's the best way to use this or connect that together. But one place I do think it's interesting is if you think about, we always sort of say with deep networks that everything's learnable, we learn everything, but we do make still big assumptions. We make assumptions about the network architecture. It's almost like a heuristic that we choose. And so what's sort of nice with this Welch-bound connection is it's perhaps giving you a guiding principle over, just say you know you've only got a certain number of parameters you can have, you need to do things in a computationally certain way. The Welch-bound can help you perhaps predict what type of network architecture would work well, but yet still give you good generalization performance. So that's sort of like one nice connection there. And then to the second question, are there different ways of inducing sparsity? There definitely are. So one way you can, sometimes people want to, if you look at image coding, for instance, a lot of stuff's been doing in deep networks there. And what they do something very similar to vector quantization on the final layer. So they use like cross entropy loss and things like that to kind of really promote sparsity in the end. But one place I think it's very interesting is if you look at most autoencoders or deep networks, what we love to do is we love to go from these big expressive signals and kind of go down to like these bottleneck representations. So it's almost like a PCA thing we're doing. We're kind of going down to lower representation. And so in the end, the hidden unit is sort of low rank. It's low rank. And so one thing I think is interesting is actually sort of saying, well, why does that have to be the case? That doesn't necessarily have to be the case. You could have something that's overcomplete, but as long as you constrain it in a way. So could you have like an L1 or a sparsity parameter there? So do we necessarily always need bottlenecks in our networks as long as we're constraining it in some way? And so that's one thing I like. I like perhaps that you can kind of swap constraints or penalties for network architecture and kind of go backwards and forwards. And so could you add that in? Does it make sense? And if anything, it just gives people a little bit more arsenal in the toolbox when they're attacking different perception problems.
Mm-hmm. Great, fantastic. Well, Simon, it's been wonderful. It was a fantastic talk. I think this is an amazing, especially for students who are watching, this is a great example of tackling a very concrete problem. And then through your solution, all these other beautiful things just popped out theoretically that apply to other things. I mean, that's as good as it gets when you do research. You know, you go for something concrete and then all these wonderful things come out. So it was absolutely fantastic talk. We're really happy that you took the time to be with us today. Miss seeing you in person very much, but I felt your energy. I'm energized now to work harder. So thank you so much for being here.
And thank you, Michael, and thank you, Liam, for having me. And if anything, I got a kick out of seeing Michael in a tie. So that was my highlight for the day. So I thought that was wonderful.
Great. You're easy to please, Simon. You're easy to please. Okay. So with that, I think we're going to wrap up the keynote here. We'll stop streaming, and I'd like to see everybody on Slack later. And once again, Simon, thank you very much.
Thanks so much, guys. Pleasure.